Galaxies need more mass. In Part 1, we saw that galaxies don't behave the way we expect, based on the mass we can see. This is known as the galaxy rotation problem. Stars at the outer edges are moving too fast to stay bound under normal gravity. So the first thing scientists did was apply the most basic fix. What if there's more mass there than we can detect? If galaxies contain additional unseen mass, that would give us the extra gravity needed to keep them stable. Why more mass helps? For stars to move faster and still stay in orbit around the galaxy, there must be more gravity pulling them inward. And more gravity comes from more mass. So if galaxies contain additional unseen mass, that could explain why the outer stars are moving so fast. But simply adding more mass doesn't fully solve the galaxy rotation problem. Not a point mass. If we just place all that extra mass at the center of the galaxy, we run into the same problem. Gravity would still weaken as you move farther out. So, stars near the edge of the galaxy should be moving slower than stars closer in, just like we predicted from the visible mass alone. That means the missing mass cannot be concentrated at the center of the galaxy. The halo idea. But what if the missing mass was spread out in a cloud, extending across the entire galaxy and beyond? This creates what scientists call a halo of unseen matter, and it changes how gravity acts at different distances from the center. As you move farther out, the gravitational effects combine differently, so the net force changes with distance. These effects combine so that the net gravity stays stronger farther out than we would expect instead of dropping off like a concentrated central mass. But this only works if the halo is distributed in just the right way to produce that extra gravity. The halo can't collapse. The halo idea can fix the gravity problem. But it creates a new question. If all this extra mass is out there, why doesn't it collapse inward over time? Gravity should still be pulling it toward the center of the galaxy. So now we need a new requirement. This extra mass must stay spread out instead of collapsing inward. That means it has to behave like an energetic, diffuse gas that barely loses energy over time. Why it's dark? There's another key requirement. This extra mass must not interact with light, or we would be able to detect it, which is why we don't see it anywhere in the galaxy. And because it does not emit light, that is why it is called dark matter. But to match all the observed behavior, it also has to interact extremely weakly overall, or it would lose energy, cool down, clump together, and collapse into dense objects. So, to remain spread out in a halo, it must stay diffuse and energized over time. And because it would barely interact at all, it would be extremely difficult to detect directly. Limits of dark matter. Dark matter can explain key observations, like galaxy rotation and gravitational lensing. But many aspects of galaxy structure, formation, and long-term stability are still not fully understood. So, while dark matter may explain part of the picture, it may not explain all of the energy patterns we see. In the next part, we'll explore another possibility. What if gravity itself behaves differently at the scale of galaxies?